thanks everybody for coming, and thank you also for the invitation. And congratulations, of course, on this exciting new school. I'm really looking forward to future collaborations, both through Nvidia, possibly, and the University of Washington. As you just heard, I'm all partially from the university, which means I'm spending actually 80% of my time at Nvidia right now, where we're establishing a new robotics lab in Seattle. We're doing basic research where we publish the work and collaborate with academia and also many interns. And this came about last year in the summer when I was at the CVPR Computer Vision Conference, and I met with the CEO of Nvidia, and we talked about kind of what are exciting areas in robotics and where is the future going. And if you look at kind of what the hot topics right now are, where already businesses are being established and things are starting to really work, is, for example, here in these settings, for example, in fulfillment centers, this is kind of the Kiva system that Amazon is using. Here's DHL, where we have delivery of packages. Lower down here, you have work, for example, Servio robots that are delivering food and other items in hotels. Also, we're starting to see delivery robots in urban spaces, and of course, the big elephant in the room is kind of the self-driving car domain, where what you can see here on the upper right. And in this domain already, Nvidia is very heavily engaged, and the idea of Nvidia is also kind of to provide, let's say, the brains, the computing that drives this kind of robotic systems. If you now look at this from a high-level perspective, and I'm sure several people in the room, my research colleagues might agree on this, that if you look at these applications that I just showed you, it's actually mostly just about getting from A to B without crashing into something. Okay, so if you think about autonomous car, I want my car to drive me somewhere, and in the meantime, it should just get through traffic without crashing into other cars, into buildings, people, hopefully even bicyclists. But we believe that actually the next generation of robots will be much more about seeking physical interaction with the world. So where the first part is really about avoiding any contact with the environment, because you don't want to crash into things. This is really about robots that seek interaction with the environment so that they, for example, can pick up objects and they can help people. And they do all of this in very close proximity to humans. So again, it's not about staying away from people, but doing this close to people and physically interact with them and help them achieve certain goals. Here's kind of a mock-up scenario of how I think it would be nice if we could collaborate with these kind of robots. This is a robot in a wet lab scenario where, for example, it would be nice if you could just show it the objects that it should care about. For example, here's a test tube in this case. So the robot needs to understand the language, what you say. It also needs to use this example to learn what the object is in the hand, that this is a test tube, colors red or things like that. Then you might want to be able just to tell the robot how it should perform certain actions. Turns out in a wet lab it's important, like how you shake test tubes and things like that. So you should just be able to demonstrate it to the robot once, and then it should be able to execute that. And finally, you want to then be able to collaborate with this robot over multi-step complex tasks, simply where the robot takes over certain steps and the humans, and you are kind of interacting in a very natural way. There are many different application domains for these kind of collaborative robots. You can see here, for example, in the elder care environment, or people with physical disabilities. Of course, the next generation of industrial robots, and finally, ultimately, also robots that really help kind of everyday people in our household achieving certain chores for us. So it's a very general setting in which we would like to enable these interactive manipulation robots. What I want to talk about here is just give two kind of areas that I think are relevant for that. We are also doing a lot of work actually on the language understanding and human-robot interaction, but I'm not going to go into those details. I think TUM is going to talk about some of that in his presentation. In the first part, I'm going to show some what we call model-based approaches, which are techniques that aim at kind of building physical models of things in the world and using those for example, for control. And then in another section, I'm going to talk a bit about more learning-based techniques, which I think are going to be very relevant for these systems. So let me start with the model-based approaches. And a lot of the work, or how we got started in this area, is with depth cameras. You can see here a stream of a depth camera. This was very early on when I was actually working at Intel at the time, where on the left side you see color information, on the right side you see distance information, depth information about how far things are away in the world, where blue means further away, red means closer. And for roboticists, of course, this is extremely exciting, because if you want a robot to kind of navigate through environments, pick up objects, it's of course extremely important that it knows where these things are. And the information on the right provides this in a much more immediate way than pure color information. So we were very excited about this and immediately started using it for example, learning models of the environment. So one piece of this research really went into building dense 3D models of things in the world that might be relevant. Here on the left you see a 3D model of, for example, one of these wet lab environments where the focus is especially here also on geometry. You can see this here. This is shape information. Also, of course, robots might want to have 3D models of objects that they have to interact with so that they can pick them up. And finally, hopefully, also 3D models of people. On the next slide, I just want to show you roughly kind of how we build these models autonomously using these depth cameras. And then I'll go into some examples of how we can actually use them for robotics. So here's some first work where the idea is you get a stream of depth camera data, and on the left you can see the 3D model of this wet lab bay as it's kind of evolving over time. And the idea is very, very simple. You build a 3D representation and you take your depth camera data and you kind of stitch it together. It's similar to the techniques when you do a panorama on your iPhone or whichever phone you want to choose, is kind of where you use this information to put it into a consistent 3D model in this case. Okay, we can do all these techniques now in three dimensions and in real time at 30 frames a second. And there are many different techniques that can achieve this nowadays. Here you can see some work where we wanted to enable a robot to actually autonomously build models of objects that it might interact with. So in this case, it has a beer can, which is of course very important, in its hand, and it's moving the can in front of the camera so that it can build a 3D model of the camera, of the object, and can it use it then in future settings. Okay, so you could imagine robot navigating around, I haven't seen a certain object, it just can pick it up and then build a 3D model of this. And finally, actually the most tricky part is building 3D models of people. The problem is people don't hold still, which means they might move, which makes it much harder than building the models like the ones you see on the left here, because there the assumption is always that the thing that you are mapping is not changing. It's a rigid object. In this case, humans are, of course, moving, possibly. So what you'll see here is, on the left side, just the outside view. In this case, the depth camera is on the laptop. And here you can see the live video, depth camera video, seen by that camera. And down here you see the 3D model of the person that we are building. You can see here that it's more or less doing a denoised version of the input information. And at the same time, the tricky part is here that we are, again, not just modeling the 3D geometry, but we have to constantly also update kind of the deformation of this object model. Okay, so this is technically the trickiest part. And Richard Newcomb, who was a postdoc with us at the time, he was able to implement this on a GPU in real time. So this works also at 30 frames a second, which of course for robotics is also always important that it can do these kind of things in real time. So now that we have object models, the question is, what could you do with an object model? Here's one setting that we're currently looking at in our lab, is, for example, where we have, in this case, it's an ABB Yumi robot, and it has a model of the cabinet in front of it. And there's a cup here on the bottom, and it wants to put the cup into the cabinet. So what you see in the lower left down here is kind of the internal representation that the robot is using to do its planning and control. So it has a depth camera that you can't see in the video, but it's somewhere up here. So it's using the only information from a single depth camera to keep track of the object, to keep track of the cabinet as it's interacting with it, and then to perform its control. Okay, so this is just an example of how we can use these kind of 3D models in order to perform higher level tasks. And of course, what we're looking at right now is going beyond the cabinet, but doing something like this in a full-blown kitchen with many objects in the environment. Here's one more example that also shows that we can do these controls in real time. So it's very nicely adaptive. So here the robot hands over the cup, and you could see that the human was kind of pushing the cup out of the way. And one key concept here is also that we're using technique. It's called Riemannian motion planning, which can very reactively, quickly recompute motion controllers on the fly as things in the environment change. So here it has to pick up the cup from the person and then stack it on top of the other cup. And again, here we are combining the motion planning and the motion control with real-time feedback so that it can react to these kind of things pretty smoothly. Okay, so this distinguishes these kind of robots already from what you typically see in industrial settings, where the assumption is that everything is under the robot's control. One setting where I think it's also going to be important actually to track not only rigid objects, but to track, for example, humans and their shape is an application domain that Charlie Kemp at Georgia Tech is investigating, working with people with physical disabilities. So this is a study he did with Henry Evans. He is impaired in that he cannot move his body beyond the neck. And they were looking at use cases, what people would like robots to do. And in this case, for example, it's shaving. I know it sounds a bit scary, but they saw that this would be a really good use case. For example, pulling up the blanket, so if he's getting cold or warm, you can change that. Or even things like holding a napkin to the mouth. And I think if we want to investigate these kind of settings, it's not going to be sufficient to be able to, let's say, just track a skeletal model of the person, but we need to know where the surfaces are. So here's one example for work that my student Aaron Walsman did, where you can see in real time here on the right side that we have a skeletal model of the person, and we are tracking the deformation of the surfaces in real time, because I think you need this kind of representation at some point if you want to, for example, shave someone or stuff like that. Okay? So far, all these techniques were what I call model-based, which means we very well designed the physics underneath the data generation, for example, light rays, and the 3D geometry of scenes. And these can work very robustly. One key limitation that I haven't mentioned yet is, for example, that these models always have to be initialized. So, for example, if the robot should pick up a cup, we first need to know where the cup is initially, and in this case, we actually just initialized it manually, but ultimately we want to be able to detect these kind of things in real time as well. So these high-level view on these general model-based approaches, the way I see it is that on the one hand, they can be very, very robust. The nice thing is, because they are just mostly modeling the physics underneath your system, is that they are very general and can be applied in many different settings. And one topic that's going to be important more and more is that they are so-called explainable, which means we understand what is going on, we can predict what's going to happen. But some key limitations is that they require humans to actually often design these kind of models, write down the equations and come up with the right solutions. They're also often just approximations of the real world, and they might fail when they are not initialized well or if the parameterization isn't correct. So that brings us to the second part, where I'm going to talk a bit about more learning and simulation. And that was also one of the things where I got very excited about joining Nvidia, because through their gaming background, of course, they know a lot about simulation. And I think simulation is going to be pretty important for robotics, so that we can automatically generate huge amounts of training data that we might need for these new learning techniques like deep learning nowadays. So one area, for example, is 6D object pose estimation, where the idea is you get a camera view on the robot. It looks at a scene. You have a 2D input image. In this case, we want to do it only based on RGB. Okay? And let's assume you have a model of an object, and you'd like to estimate the 6D pose of where that object is, which means its 3D location and its 3D orientation in space. And doing this just from a camera image, and doing this with purely, let's say, model-based approaches is extremely hard. At least I haven't seen any solution to that problem, and that is kind of where techniques such as deep learning have shown to be very, very successful. This is just one network that we developed. There are many different networks out there that can do this kind of work. So I just want to give you the high-level idea, where the idea is you input an image of the object that you have trained on, you feed this through your network, and then the output, in this case, for example, might be a bounding box model of the object that is oriented in 3D. And in this case, the network needs to learn to detect these corners of this bounding box. In order to train these networks, the key problem is you need to generate a lot of training data, which means you need to give it many images of the input of the object and the desired output pose. And doing this manually is just a very, very tedious task. A traditional way of doing this is you put these objects in a scene, and then you go around with a camera, and you do this many, many times. Here we did a data set that I think had 92 videos, which means 92 times you move it around, you change the lighting conditions, and use that as your training data. And that works, but it's actually, first of all, very, very time-consuming, and at the same time also it doesn't cover enough lighting conditions sometimes. So one approach that we just developed that works actually very, very well is just randomly generating data through simulation. In this case, you have 3D model of the object, and you just randomly throw these objects into the scene. You change the lighting conditions, the appearance. Since it's simulated, of course, you know the ground truth locations of these objects. You might also even look at scenes that are a bit more physically accurate. And then you train a network just on this data so that it learns to go from an image to a 60 pose estimate. And here I just want to show you some examples of how this now works in different lighting conditions. We're still working also on improving the accuracy, so we have some other research, but I don't have time to go into this. But I think this is already very impressive if you look at how different the lighting conditions here are, that the system can really pretty accurately detect these objects and estimate their pose. And that network has never seen a real image during training. It was all simulated from photorealistic rendering. And down here you can see how we can use this then to get the robot to pick up objects and things like that. In general, I think simulation is going to be very useful. Here on the right side you see an example of a system that Nvidia is building right now, where we can now just run these systems that typically work on a real robot and operate them also fully in simulation, and we get behaviors that match the real world actually very well. So the idea now is that you can use these systems to, for example, improve the robustness of your controller or test out different even hardware systems and things like that. One other example or advantage of simulation is, of course, if you want to do large-scale training. In this case, one hot topic is deep reinforcement learning. Imagine you want to train that robot on the right to get that little tube into this hole, the pack-in hole, but now the problem is it's on a rope, so it's swinging around, you don't know the mass exactly. So in this case, we can train a system here in reinforcement learning on the left side, where, for example, on a GPU, you can just run hundreds of them in parallel. And then you train your reinforcement learning controller, and then after you pre-trained it, you run it on the real robot, and there's always a discrepancy, so you can use this real data to refine your simulation then, and in the end you get a system that works reasonably well on the real robot. In this case, again, we did not know how long the rope is. The only tracking that the system is performing in this case is really just of the position of that little cylinder. And we put it in a tilted position also, the hole, so that it's a bit trickier. I should actually only show you the second example next time because it's more impressive. The first one was a bit harder. Okay, so then also other simulation examples is for manipulation, right, where we now can actually simulate, this is an Allegro hand, we can simulate the forces and things of deformable objects. We can use the same kind of simulator here again on the right side. Imagine you want to train a deep network to grasp arbitrary objects. You can now generate thousands of objects, and for each object you can exhaustively try all the different grasp points and then test them in simulation about how well they work. One final setting of this, how we can use simulation, is of course for robot training. This is something they demoed at GTC in the spring this year, where on the left you see the VR setting, on the right hand side you see real-time simulation. Okay, so he's controlling the grippers. And you can see the simulations actually, it's pretty nice, photorealistic. The behavior of the dough is reasonably good. It's not perfect, of course. But you can imagine that that can be really useful for training robots. And in this case, the task is, of course, the crucially important thing of making pretzels. Very important. But again, I think this kind of setting can really make it much easier to train robots to do certain tasks. Okay, with that, I'm going to come briefly to the discussion. First of all, I think over the last years, we've seen really tremendous progress on the sensing side, on the hardware side. Something I didn't mention is also touch sensing on robots is going to be extremely important, I think, and we are seeing good progress there as well. Also, of course, computing, highly parallel computing, And deep learning advances make robots much better at detecting objects, reasoning about objects, and also people. And I think we will then be able to have robots that can really collaborate with people and support them in complex tasks. And there are many different application domains. If I get one final minute, then I just want to mention one aspect that I think also food for thought, maybe for discussions later on, is that so far I showed you all these objects are actually kind of designed to be as accurate as possible, right, and as accurately on the physical side. So if you look at what humans do, this is Julia Child. She's a very famous cook in the US. And here she's demoing certain things. And when we look at this, we have a clearly intuitive understanding of what is going on, right? So on the right side, for example, chopping the onion. Not that we could replicate that, but at least we see, okay, the onion is sliced, and then you have these different rings and things like that. Or on the left side, she's making dough, so she's mixing liquids. They have a certain behavior. You can now move them from one container in another. And in robotics, we just don't know how to do these things yet well, right? And the question is, should we even aim at building highly accurate physics-based models for this, or is there an alternative approach that goes a bit closer to kind of the intuitive reasoning that we humans are performing when we reason about things like gravity or how things behave in the real world? So I think humans are a really good inspiration here for maybe the next step where we want to have robots that do perform lifelong learning. I'm not going to go into all the details on this slide, but lifelong learning and also combining deep learning with these model-based techniques to come at something that maybe also has a robustness of human behavior, which I find truly amazing what people can do compared to what these robot manipulators can do. I always, when we sit at the dinner table, I always tell my daughters, like, imagine a robot could not do this, right? And they're always, oh, Daddy, I know. But it's really fascinating how easy these things are for us, right, compared to where we are in robotics still. So there's still a lot of work to be done. Thank you very much.